many of you, maybe all of you know, she was here in Heidelberg for a long time, did her studies here and the PhD, and also went to Cambridge in the meantime. And after her PhD, she went to the Munich area to work at ESO, and was there also a staff member at ESO. But recently she won a very prestigious award, so to speak, with the Max Planck Research Group, which is an open competition thing for where you win that, you get money for your own group for 2 or 3 people. And she's now setting up the group as of September this year at the Max Planck Institute for Astronomy here on Colloquium. And so it's really a welcome back in that sense, because she's going to be here doing great research with her own research group. So, yeah, I would say enough said, and we're of course very much looking forward to your talk.
Okay, thank you very much, please.
And so let's welcome her back.
This is a tremendous pleasure for me to be on this side of the table, or now, because I've seen many colloquia from the other side, and it's a great opportunity now that I start with my new group, with my new position here, to introduce to you the kind of research we're currently doing on nuclear star clusters and black holes, and also what we're planning to do over the next couple of years. So I would like to start my talk with a little motivation, introduction. Why am I looking at what I'm looking at? Why do I work and what I work on? And then give you an introduction on what nuclear star clusters are, why I think they're interesting when you want to look at black holes and black hole formation, and then also look at specific objects and use the Milky Way as a reference object. So that's why I would like to start with the Milky Way, and maybe we can lower the lights a bit. Because the Milky Way is in many respects the perfect local laboratory to look for physical processes. So the Milky Way is a normal galaxy in many respects, and what makes it special is it's our own host galaxy, so to say. But we are sitting in a disk of the Milky Way, and when we look towards the center, here you see the bulge of the disk. You see, and especially now that it's so dark, there is a lot of dust in the foreground. We basically look through the dust lane, through the dust layers and in between the spiral arms, and it's quite hard to look at the very central region. So in order to look at the center, we need to go to near-infrared wavelengths to pierce through the dust, and then we start to see very interesting things happening. And actually the center of the Milky Way, we have the best studied massive, supermassive black hole in the universe. So we are now flying into the center of the Milky Way through the dust. We switch wavelength, we look in the near-infrared K-band, and at some point you start to see a very massive cluster here popping up, and you can even zoom further down with using adaptive optics to overcome the atmospheric blurring. And the group led by Reinhard Genzel and Garching has monitored the motion of stars around the center of the Milky Way now for 20 years. And this is a simulation using the motion of the stars, the resolved motion of the stars, and overlaying the orbits, and like having a 3-dimensional model of how the stars move around the unseen mass of the central black hole. The black hole in the center of the Milky Way is 4.3 times 10 to the 6, 4.3 million solar masses. And as I said, it's the best confirmed case of a supermassive black hole. But it's not the only one. We see many black holes in many massive galaxies, and actually every time you look at the center of a massive galaxy, you will find a supermassive black hole. Here, another famous example, M87, the central galaxy in the Virgo cluster. And here, when you plot that on the black hole mass, on the y-axis, and the bulge mass on the x-axis, here is where the Milky Way falls, and here is where M87 falls. And Especially with the advent of the Hubble Space Telescope, with the superb spatial resolution that the Hubble has, this area got filled in very rapidly in the 90s and early 20th century. And you find a very strong, tight correlation between the mass of the black hole and the mass of the bulge. And this has actually been my diploma thesis here, and I was still called Heidelberg at the time, and it's already 10 years ago, so time really flies. And this relation has, of course, evolved over the years. Many more pointers have come to it, but still, it's been, and it's not only the black hole mass correlates with bulge mass, there's many, many other galaxy properties with what you can correlate the black hole mass, and they give equally tight correlations. But I could give an entire talk just about this topic, which is the best relation, what can they tell you. But I would like to just mention that it has been thought that this hints towards the co-evolution of black holes and galaxies. Because the black hole and the galaxy, they live on totally different spatial scales. The black hole is in the very, very center, and it actually doesn't really know or doesn't feel the influence of the stars surrounding it. Likewise, the stars in the bulge, they're not influenced at all by the mass of the black hole. They just move on their orbits, and they couldn't care less about what the black hole does there. But still, you find this tight correlation, and that has led people to think that there is some evolutionary connection between the two. But what I'm interested in is actually what happens here at the lower mass end. What happens if you cannot actually measure the mass of the bulge because you have no bulge? There are pure disk galaxies in the universe. What's going on there? Can they tell us something about the seed mass for black holes? Can we really find out how black holes get to the centers of galaxies? Because when you grow galaxies, you merge the disks, you merge the black holes, you grow bulges, and you move up to the sequence. So the sequence actually gets tighter, and there is this theory that it's connected to the central limit theorem, that you just, with more and more mergers, you make the correlation tighter. This has been shown by Knut Janke and Andrea Macho, and simulation goes back to early ideas of Chen-Peng. But as I said, it's a different talk. I wanted to find the seeds for the supermassive black holes. So the question is, are all galaxy centers special? And are there always black holes? And if so, why would there be always black holes, or maybe not? Let's see what we can say about this. And as I said, very important objects in that respect are actually bulgeless galaxies. And when I say bulgeless, I mean pure disk galaxies. So these are galaxies that have not yet undergone any major merger event. So they still have the pure disk structure. They're totally, they're totally supported by motion in the disk, not random motion. So they're at the start of the evolutionary sequence of this merger scenario. And when you look into the center of bulgeless galaxies, what you often find is a nuclear star cluster. And when we're zooming into the center of this very nearby example, NGC 300, at a near distance of about 2 megaparsecs, and now switching from ground-based to, again, HST resolution, you find a very massive, compact, luminous cluster at the center. This is the nuclear star cluster. It's the most luminous throughout the entire disk, and when you look at the surface brightness profile, NGC 300 has a pure exponential disk out to 10 scale lengths, so this is really a pure exponential, but the nuclear star cluster sticks out 5 magnitudes above the disk, so this is really the most brightest thing in this galaxy. So now a bit of the introduction of what nuclear clusters are, where do you find them, and actually they're detected in about 50 to 75% of all galaxies. So in pure disk galaxies, they're easier to be picked up because they just stand out above the background. But they are also found in bulge-dominated disks, and here's a couple of papers, and here recently, Iskren Georgiev and Torsten Böcker, they have digged through the entire Hubble archive and pulled up a sample of over 220 galaxies where they identified nuclear clusters. And from that, so here about the occupation fraction, so the fraction of galaxies, so you find them in small ellipticals and S0 galaxies, also bulge-dominated disks, but also pure disk galaxies. They have very comparable half-life radii between 2 and 5 parsecs, so they're comparable in their size to globular clusters, but they're actually more luminous and more massive than globular clusters. And this is work I've been doing a few years ago, where we wanted to see whether they actually truly sit at the center of galaxies. So we looked at the velocity maps of the galaxy by Torsten Böker's early sample, and we looked where is the dynamical center, where is the center of the potential well, and actually the nuclear cluster sits there. And this is a special location, of course, in the galaxy because the material would eventually sink in there. So this is one of the ideas, that maybe the clusters form in the disk and they sink to the center. But what you also see is that you form stars in multiple events. It's not a single event. It's not that you just form clusters in the disk and then you pull them down. But you have also young stars on top of the old population. Because when you have integrated spectra and you fit them with the stellar population models, a multiple age fit is always a better fit. So you have recurrent star formation in these. And it's probably not surprising because of their special location in the galaxy, because they accrete new gas and can make new stars. And it's been seen by different people also in early type galaxies, recently by Maria Luminova and collaborators. They have masses that are more massive than globular clusters. So here you have the secret, you have the surface mass density against mass of the system. Here you have globular clusters, and the nuclear cluster, they really sit at the highest mass end of this relation. And here you have bulges and spheroidal galaxies. This plot has been updated now many times, but this is by Ingo Miskel and Michael Hilker, and you see it's much more populated. Here you have many more globular clusters, but the nuclei are really at the highest mass and highest density end. So they have similar sizes to globular clusters, but they're much more massive. They have much higher stellar volume density than globular clusters. And actually that's a point that is very important, because if you want to look for black holes in nuclear clusters, it's important to have high stellar density close to the center, because they would make an imprint on the dynamical signature for a black hole, because you have more orbits closer to the center, and that's why you get an enhanced signal. And as I said, there is in the Milky Way, we have a nuclear cluster. This is actually the nuclear cluster of the Milky Way. And we have the best studied supermassive black holes. So they do coexist. We have black holes inside nuclear clusters. We know that from the local reference of the Milky Way. And when you look at the Gannon-scaling relation, mass of the black hole versus velocity dispersion of the host system, here is where the galaxies lie. And here we have put constraints like upper limits on the masses of black holes, what you could hide in the sample of Jakob Balcher, and you find that it's not a fit, it's just an extrapolation of the relation. So it seems there is something between the host and host dispersion and the black mass of the black hole that may be inside them. And this is the point of omega sen, and I just discussed this today with Laura Watkins, because Glenn van der Ven said that they have done new modeling, and Laura is actually working on this. And this is where their new measurement for omega sen, if we would really find a black hole omega sen, which still means it's very much debated whether there is one or not, but it would lie just here. So the key questions that I'd like to address is, are nuclear star clusters connected to black holes, or what can they tell us about black hole formation? And as I said, it's especially interesting to look at the low mass systems and look at whether we can find black holes in bulgeless galaxies, because the occupation fraction of black holes in low mass galaxies actually is a key observable to discriminate between black hole formation models. And I would like to tell you a bit more what I mean by this. For black hole formation in the early universe, there are actually two competing scenarios that are hanging around. First is the direct collapse model. So in the early universe, you collapse the matter directly to form seeds that are about 10 to the 4 solar masses or so, roundabout, and you would populate a few halos with those kind of seeds. Or the competing scenario is that you have many population 3 stars. They have seed masses of around 100 solar masses, but you would have many, many of those. So all your halos are populated with those, and then you go through your merger and galaxy growth sequence, and you grow black holes through accretion and that. And what you would get out in the end is that in this case, with the high mass seeds, you have that 50% of all nowadays 10 to the 9 solar mass galaxies host a black hole that is of the order of 10 to the 5 or larger. And in that case, you have that 90% of all these type of galaxies host black holes that are 10 to the 4 solar masses or larger. So when you look at the scalar relation again, your black hole mass versus velocity dispersion of the host, this is for the high mass seeds and this is for the low mass seeds. So here you have, as I said, you have a few at the very lowest end, but they have higher masses, and here you have many. This fraction is almost at 100%. And you have lower mass black holes. So this is one thing that I would like to constrain, is really, can we find those low mass black holes to constrain this formation? And the second question is just, how do nuclear clusters form and grow? Because this is still debated. There are again 2 competing scenarios going on. The one is the star cluster infall merger. So the clusters, they form somewhere, and then they merge they fall due to dynamical friction to the center. They merge, and they will build a nuclear star cluster. Or you have the scenario that you really have the cluster formation in situ, so everything forms at the center. But likely it's not either or, but it may be a combination of those 2 scenarios. So this is the thing that we would like to constrain with our ongoing survey. So what is our ongoing survey? So we want to study the morphology, and we have HST imaging for all the objects. We want to study the stellar populations through optical spectroscopy, and the kinematics through resolved integral field spectroscopy. So we have adaptive optics, integral field spectra. And for the northern sample, we have NIFS on Gemini, and that's been led by Neil Seth. And I'm leading the southern part of the survey with Symphony on the BLT. This is the sample, and it's basically a complete sample of the nuclear clusters out to 5 megaparsecs. And we have added another interesting case that I will tell you more about later. It's at around 6.6 megaparsecs in distance. So this is the disk. Well, we have, you see that we have pure disks, but we also have early type galaxies in the sample. This is the pure disk part of the sample, where we have also new UC3 imaging led by the Bart. So on top of these ground-based imaging, I'm now putting here the nuclear clusters, and so you can see them a bit better. I've lined them up. So here are the clusters, and we have 7 filters with UC3. So we have UV, UV, B, I, J, H band. And what you can see is, so here you always see one cluster in the different filters. Here's the names if you want to pick up one of those. What you see in basically all of them is that the cluster size increases with the filter wavelength, right? So in the UV, it's quite centrally concentrated, but in the reddest filter, you have them quite puffed up. So the younger stars, they sit at the very center, and the older component is especially much more extended. And that's actually something that we also see in the Milky Way. So the young stars, they sit at the very center, and I'm now coming to the Milky Way. So this is a kind of a family portrait of nearby clusters, and I put the Milky Way here among the others. So just zoomed in a bit. So they look alike. They are similar type of objects. And in the Milky Way, because we look actually through the disk, it's quite tricky because there is a lot of dust extinction still in the mid-infrared, and this is a study led by Anna Schroeder, where we looked at the properties of whether the cluster is flattened or whether that's actually only mimicked by the foreground dust, because there is more dust in the southern part than in the north. So but here Rainer has done an extinction correction, and he's measuring the flattening half-life radius, and it falls right among what other external nuclear or nearby nuclear clusters have. Effective radius of 4.5 parsec, and the mass is 2.5 times 10 to the 7 solar mass of the nuclear cluster. And to remind you, the black hole mass in the Milky Way, very accurately measured, 4.3 million solar masses. And now when you look at what is the fraction of the black hole mass compared to the total mass, so nuclear cluster plus black hole, this is about 15%. So the black hole makes a good fraction of the total central mass. And as I said, we have integral field spectroscopy for all of this. So we have velocity maps for all of these clusters. So this is an edge-on example, and here more face-on, HSC 7793. And what we would like to do is actually get the same type of observation for the Milky Way. But that's quite tricky, because here you see all these adaptive optics IFUs. They have a field of view about 3 times 3 arc seconds. And they are just a perfect match to the nearby nuclear clusters. But this is an area of like 4 arc minutes, or is that right here? Or 10 arc minutes. We do 4 by 4 arc minutes, right? And that's why, because we would like to observe the Milky Way nuclear cluster in the same way as the external ones, we cannot use ready-made IFU. We are making our own IFU observations, because we put a long slit here, and we scan over the cluster and read out while we drift. And we do a drift scan, and this is the PhD thesis of Anja Feldmayer. She's working at ESO and working with me here, so she's visiting every once in a while, and she's studying the assembly history of the Milky Way nuclear cluster. And with this drift scan, she could put together a type of IFU observation, and the goal of the thesis is to study the formation history of the Milky Way nuclear cluster, but also test black hole mass modeling that are used for external galaxies. In the Milky Way, we know what the black hole mass is from the resolved orbits, but in external galaxies, this is the type of data we have to get this type of measurement. So in this case, this is a great reference sample, so to check the models whether they actually give the correct result. And as a comparison, the same, more or less same area, also in the edge-on example. So you see there is rotation. You see the red parts are going away from us, the blue part is coming towards us, and we have not only velocity map, but also velocity dispersion map. You see the rise in velocity dispersion, exactly where Sagittarius A star is, where this cross is, and the radius of influence of the black hole here is about 60 arc seconds. So you see that kind of elevated velocity dispersion is more or less tracing the radius of influence of the black hole in the Milky Way center. What I found in the data set is that the position angle of the kinematics is actually not aligned with the galactic plane, which is here, that it's offset by 9 degrees. And what we also found is that you have confined, perpendicularly rotating substructure that is not rotating with the bulk of the other stuff, but it's really perpendicular to this. And both this misalignment and also this hints towards a cluster infall scenario for making up the nuclear cluster. From the same data set, I also extracted individual spectra of the brightest stars. And here you see the color coding is the CO magnitude. And it gives a proxy for the age of the stars. So the blue are the younger stars, and the red are the older stars. So you see that the younger stars are also very centrally concentrated. And in this data set, Anja could also pick up new young stars that have not been known before. On top of the ISAC data that I showed you just now, we have also acquired new KMOS data. The ISAC data was limited by a limited wavelength range of the observations, but with ISAC we have the entire K-band, so it's easier to observe, to age date the stars and to get stellar population. So this is the central field, KMOS, compared to what we had as a spatial resolution with ISAC, so it's much better. We can pick up many more individual stars, and this is a result that I just produced now, where we have the known young stars at the center, and these are the new young stars that she could identify. So when you put that in perspective, where this field actually lies, it's very central. So the young stars are at the very center, and around here, if there were young stars, we would find them, but somehow they are not there. Good. So, as I said, we have velocity maps for all of those, and one of the ideas is to get black hole mass measurements in those. And I'd like to show you one of the examples that I find particularly interesting. It's the nearby bulgous galaxy NGC 3621. It's an interesting one because it actually hosts a nuclear cluster plus detected AGN signature inside the nuclear cluster. So when you look at the diagnostic diagram, and this is the same in the mid-infrared, looks the same, you see that the central ionization is actually in the region of the AGNs. So if there is an AGN, it has a variable X-ray source at the center, and from the X-rays you can get a lower limit on the black hole mass, and we get a high upper limit from the black hole mass due to ground-based, seeing limited integrated velocity dispersion measurement, where you can vary the black hole mass and the stellar mass to light ratio, produce a dynamical model, and this is the allowed area where the model can lie. And when you put zero mass into the stars, so everything would be dominated, the kinematics would be totally dominated by the black hole. This is a firm upper limit of 3 × 10⁶. So these values bracket basically the true value. A more realistic mass to light ratio would be somewhere around here, so it would be just below 10⁶ solar masses. We observed this cluster, this nuclear cluster with symphony, and we have produced a dispersion profile, the velocity dispersion, or actually it's the group means square velocity, so it's rotation plus dispersion as a function of radius, and we stitched together different scales of symphony and Argus observations, and plot on top some dynamical models, with Jeans models are these, and we actually detect, because this is the zero mass black hole case, and we detect the black hole of 7 × 10⁵ solar masses. And this is actually the first dynamical detection of a black hole in the bulgous galaxy. And yeah, so we have the same type of data for all of these. Maybe not all of them are such good candidates, but there is another one. This is NGC 4395. It also has confirmed AGN, so there are black holes sitting in these galaxies. And they have masses, say, around 10⁵ solar masses. This is M33. M33 has a very firm upper limit on the black hole mass of 1,500 solar masses, but definitely we would like to go back and look at the maps and try to model this to see whether we can confirm this. So basically we think that there is no black hole in M33, or we can at least put a very firm upper limit on that. So what could you do, or what happens if you put those type of galaxies in a merger simulation and you kind of strip off the surrounding galaxy? Could you find stripped nuclear star clusters? And it's another very interesting project we were just finishing, because ultra-compact dwarf galaxies they are thought, or at least some of them are thought to be the stripped leftovers of galaxies. And I showed you this plot before, so here are the nuclei, and in between the galaxy sequence and the cluster sequence is actually the sequence of the ultra-compact dwarf galaxy, the UCDs. Another update of this plot by Mark Norris and collaborators, because they explicitly look for these type of objects in their Ames survey, and they're bridging the gap between galaxies and star clusters. What you see here on top of this plot is the simulation done by Joel Pfeffer and Holger Baumgart, where they actually do exactly this. They take nucleated galaxies and they strip off the body of the galaxy, and this is where those galaxies would end up, or the stripped nuclei. And recently, we looked at an interesting case, and actually this is an overview of the Virgo cluster. Here is the central galaxy M87, and this is the galaxy M60. When I prepared this, I was looking for an image of the Virgo cluster, and I got surprised how big the Virgo cluster really is. I had to remind myself it's really huge. So you don't get an entire image of the Virgo cluster, obviously, but you get only parts of it. So this is the central region of the Virgo cluster. This is M87. And you can also zoom in to this region, M60. It's actually the third brightest galaxy in Virgo. And this is how it looks like. It also has a companion, but they apparently don't interact gravitationally so much. Now, but what is interesting in this image is not neither of these two, but this tiny little dot here. It's been discovered in archival HST data last year by Jay Strader and collaborators. And it's been termed the densest galaxy, because this has really high stellar density. And if you look at, I was looking this up in this plot where it would fall here, and it would actually be like right here. So it has a mass of a few times 10 to the 8, and is at almost 9 times 10 to the 4. So it's really right here. It's really the densest galaxy. And yeah, it's the ultra-compact dwarf galaxy, UCD1 and M60. So we went and we took adaptive optics assisted integral field spectra, again with Gemini North, and resolved the kinematics of this galaxy. And you see here the data in velocity dispersion, and you see a very peaked rise of velocity dispersion that goes above 100 kilometers per second, which for ultra-compact dwarf is really something very big. And this is the model. So we modeled this with Schwarzschild. This is done by Remco van den Bosch here at the Max Planck Institute. And the model fit the data perfectly. When you look at the contours, a black hole mass versus mass to light ratio, and this is in G-band because the image is in G-band, you find the best fit black hole mass of 2.1 times 10 to the 7 solar masses, a total stellar mass of just about 10 to the 8 solar masses, the mass to light ratio of 3.6, and again, the black hole mass makes up about 15% of the UCD's total mass. So, because there was always this, the two competing scenarios, again, UCDs, maybe they are just the upper end of the stellar cluster sequence, they're just the most massive globular clusters. But in this case, because we find the black hole in a UCD, we think that in this case at least, it is a stripped nucleus of a galaxy. And what we've also done is take the moving square velocity against radius and check whether with the genes models we can also get the same mass. And this is the best fit black hole mass from genes model, so it's totally consistent with the Schwarzschild model, and the mass to light ratio is also consistent with what the Schwarzschild model gives. For the zero black hole case, we get a very high mass to light ratio that is basically unphysical in the stellar population of this galaxy, of this UCD. So this is a simulation of how this thing could have been formed. So a merger of smaller galaxy with the M60. And just after around 500 million years or so, you kind of have stripped off most of the material, and you stay with the central nucleus plus a bit of an envelope very still there. So you can reproduce this type of object in a simulation like this. Okay. So then finally we were happy to have this accepted as a letter in Nature, so you are happy to have this Nature paper. But then the media picked up on this, which is nice, but what they were claiming is that we have discovered a black hole in a dwarf planet. And then you think like, oh, damn it, so maybe they just didn't get what we wanted to say. So maybe planet science is still sexier than black hole science, I don't know. Whatever. So, but it brings me basically back to my key questions that were like the buildup of galaxy nuclei. And I wanted to remind you that what I said is that the stellar light from the nuclear clusters can tell us when and how mass got accreted into the center of galaxies, because that is imprinted in the stellar populations, so it's not done in a single event, but it's recurring accretion, recurring star formation. And another interesting question that has not been solved and addressed yet in full depth, and that we're planning to do, is actually why some galaxies not have nuclear clusters. Because 70 or more than 70% of the disk galaxies have it, but what prevents cluster formation in the rest of the galaxies? And this is something we would like to also study. And yeah. Then for the formation of supermassive black holes, I want to remind you that the occupational fraction of black holes in low-mass galaxies is actually one of the key observables to discriminate between these formation models. So I think I'm actually earlier than I thought, so I'm just coming to my conclusions. To tell you that nuclear star clusters are actually very common objects. They are living in more than 65 or 70% of all galaxies. They sit at the center of the potential belt, so they have very specific position in their host galaxy. They have the highest stellar densities in the universe. They coexist with black holes, and they may actually explain the most massive UCDs in globular clusters. So not only the UCDs may be stripped of nuclear clusters, but also some of the most massive globular clusters in our own Milky Way, like for example Omega Cen, or definitely M54, which is the nucleus of the Sagittarius dwarf. They are definitely, or Omega Cen is not, but M54 is definitely a strip nucleus. And the Milky Way nuclear cluster serves as the perfect global reference. We can do many interesting studies there that should tell us a lot about how it looks like in external galaxies. And there are more dynamical black hole masses to come from our sample. So that's it.
Thank you, Nadine, for this very interesting talk. And so let's make a light and then open for questions. Let's first start with the students' postdocs. Are there any questions?
You were mentioning that some of these clusters are basically the leftover of strict galaxies. What is the terminology?
That's a good question. So it's probably been merged with the tornado of the other bigger galaxy. So I think it just it's the systems they merge. Also the halos merge, right? So they would.
Because there is much denser than the rest.
Yes, exactly. So I think that these galaxies, they actually probably they don't have very peaked dark matter halos. So That's another thing. With bulgeless galaxies, the usual NFW halo profile doesn't work so well. So, yeah. But this is basically, it's not my expertise, so I would be happy to have people that do dark matter halo or emergent simulation simulate this in more detail. I'm not even sure that in this simulation by Heidelberg, I think he has not included any dark matter halo in this simulation. It's just been, this simulation is not being used for the science, it's just been used for the illustration purposes. So we have not published this, that is like any constraint on the time scale of this merger. It's just been for PR purposes, so that he has done n-body simulation in emergent systems.
Okay, yes.
You mentioned that these investigations can help to answer the question how these black holes form. So these two scenarios you mentioned, but I mean, is there progress in this regard? I mean, you find these black holes with masses of 10 to 7 solar masses. Does this speak against the population 3 stars as a seeds, or is it an over-interpretation?
So unfortunately, it's not very. It's not a super well strict constraint, right? That once we go down, and maybe we need bigger telescopes actually to go further down and actually look into the clusters and see whether we find lower mass black holes even. I think a black hole of 10 to the 7 will not help you to discriminate, as you saw, because first of all, you need statistical sample, a larger sample than what we have. But I think it's still interesting to see that black holes already exist in bulgeless galaxies. So there must be, they don't grow only when you do this merger sequence, but they are there before you grow the galaxies to larger systems. So maybe the nuclear cluster itself could be one of the birthplaces for black holes due to this very high stellar densities. You have collisions. This is one of the ideas to create massive black holes, or to go from the stellar black holes to intermediate mass black holes, and then you grow them a bit further, is stellar collisions, or collisions of the remnants in the clusters. But there is also not, it's not conclusive at all whether it's either or. But I think it's actually one of the things in the right direction to look for those.
Are you able to do variability studies yet? You have enough focus on data to see if there's a lot of CDs there that indicate emerging stars?
So we have only, like for our clusters, we have no time coverage. So we have taken the data at a single epoch, so to say. But why would you need variability studies? For what would you like to have that?
Oh, I don't know, I didn't realize that additives were able to run such tight orbits that are like a couple hours or something. So that seems like how you could get stars to merge to make black holes.
Yeah. So one thing, like one other line of research that's going towards that looks for low mass black holes is indeed variability studies. If you have like mini AGN, so to say, in the center, you accrete things. But I think there you need really surveys like LSST to come online to have really good time coverage, because those would probably have variability in very short time scales. And that's currently not feasible.
Okay, let's open for everybody.
For those objects where you have all the angular resolution you need, and place the nuclei and the sigma versus electricity problem really down.
Okay.
Do the nuclear clusters appear to be rotationally flattened, or are they always sustained by pressure?
They are rotationally flattened, actually. They have quite a high.
Does that match with the distribution of angular momentum that you see in the surrounding disk? I mean, for those bulgeless sources, where you actually have gratuitous and the nuclear cluster. Is that sort of the velocity distribution in the outer particles compatible to what you see in the inner parts of the disk?
I haven't checked this for all the galaxies, but I think, well, for the nuclear cluster, we looked at this, and it's definitely rotationally supported, and it matches also the rotation of the surrounding disk. But this is something definitely we have to look into when we publish the whole kinetic sample. I think it's a very good one.
But just may I have to sort of ask if you were to speculate, if there's a continuity in the kinematic properties, would you think you were able to predict whether or not the holes, black holes in the center, would then sort of couple to the angular momentum distribution that you get to the center parts of the structures? So I mean, that's ultimately what you're sort of thinking, and to argue that there's a connection between nuclear structures and
I think I have to take this one. So you mean that the black hole grows from the matter from the nuclear cluster?
I mean, it's a question, since you argued at the beginning that there might be a connection between the black holes and the immediate vicinity between the nuclear star clusters. And of course, one interesting question, given all that work that's being done, whether or not black holes are actually spinning, supermassive black holes are actually spinning, you may wonder whether or not the most likely feeding mechanism, which is the central part of the nuclear cluster, actually then transfers into the momentum of black holes.
Yeah, okay.
So that appears to be the main action mechanism of transferring angular momentum that it does. And the occasional star is running into that from the particles, so contributing angular momentum-wise to the axis in a sense towards the black hole.
But definitely the fact that nuclear clusters seem to rotate, and we see that also in the more elliptical hosts, it actually tells you that it cannot be just merger from random directions, from halos or the globular clusters, but it has to be accretion of clusters that form within the disk of the galaxy. And that would then retain the angular momentum and form a rotating
Right,
disk.
that's what I understand. The interesting question is how much of that can feed in.
Yes.
It's the same problem that you had in Star Formation 40 years back when people were wondering how they transfer angular momentum down.
Yeah. But then we would also need to know the black hole spins, right? And then we could,
So
but that's another problem. Maybe we can solve it.
Puzzled by my questions. One is, why would these structures with a very high density and a small size so would they evaporate?
Evaporate? Yes. With the black hole, or?
So I'm really puzzled what their lifetime would be.
So, well, the nuclear cluster, the Milky Way, the oldest stars are really several million years. And you have, also there, you have multiple generations of stars. You have recent starburst that is just a few million years old. So, and, well, it lives, right? And you have a massive black hole there. So,
Can you draw any conclusions from their existence? I don't really know what their lifetime is. It's about regular people that this means that you can show. So I'm wondering what the evidence of their existence.
So what is actually the interesting point is that the effective radii of the nuclear clusters is more or less the radius of influence of the black hole. So I think there may be some equilibrium radius that actually is then stable against evaporation. Because I understand that you say that the three-body encounters should expel any of the stars, but then again, the stars, they don't get so close to the black hole anyways, right? So you have, they're also stabilized by random motions, and I think that, well, obviously it is a stable configuration, but I haven't done any modeling to test this.
The other point I was puzzling about, if you feed the black hole, would you expect high time there in X-ray vision? So I was wondering if you have an X-ray signal.
So in one of the ones we have an X-ray emission, we have X-ray signal, and Yeah, definitely you have X-ray emission from the feeding of the black hole. And this is one other line of study that is looking for black holes in small galaxies, small elliptical galaxies, is the Virgo survey, for example. And just recently they published a paper where they could put a lower limit on the occupation fraction on their galaxies, which is about 20%. 20% of their galaxies, they have definitely black holes, and then they have to push up the limit. So they find variability, and from that they can constrain black hole masses.
Can I have one more?
We recommend you time.
Yeah.
In the case where you see X-ray emission, we have been between the X-ray lines that could be the momentum of the black hole.
That I'm not aware of. I will have to look into this. We can discuss this.
I was asking myself whether rotational support of the cluster could actually be a means of hiding some of the black holes. If you look hold on, and the whole thing is rotationally supported, you won't see any trees of. So this could perhaps hide secrets of black holes.
Maybe it could, yes.
Take into account the statistics.
So right now we have pretty low number statistics in the sample anyway, so we look at individual cases and we have to model all of them, but this is actually work that is ongoing and we will do in the next couple of years. So we can discuss this once I have more numbers there. But I agree that when you have...
So you showed a lot of evidence that these clusters possibly go through accretion of clusters. And then you also mentioned that these diskless galaxies don't seem to have very cusp dark matter fields potentially. So is it at all surprising that you form such dense clusters when you don't have such a great gradient in the potential? Like if this is the mechanism that builds them up. Is it that our densities at all?
So actually the density argument is one argument against only cluster merging, because when you merge globular clusters, you cannot make something that is denser than the initial globular clusters. You have to have something that is dissipational, so you have to lose angular momentum basically. So that's why in situ star formation will make your object denser. And that's, I think, what happens. That's why I'm convinced it's a combination of both things. Because all observational constraints, so we have constraints that hint toward cluster, like cluster infall, but other constraints like density are used for also in situ star formation that make the clusters denser. Then you have, for example, you have higher metallicity in the central clusters than you have throughout the globular cluster population in the galaxy. So that tells you that you have to have some enhancing of the metallicity there. So you have to focus that later. And so I think that the density tells you that there is more than just cluster merging.
How much gas is there in this thing based on star formation, dynamical mass, the lines you get from the spectrum?
How much gas? Like molecular gas? So in some of the galaxies we do see molecular hydrogen emission, but in some others we actually don't see anything. So well, in the Milky Way center there is a lot of gas, right? There is currently not so much star formation going on, so I cannot tell you numbers,
Not a lot.
Yeah, there's not so much gas.
So you say these are the densest stellar systems, so that's what you get when you divide the total mass by the size squared, right? So if I look for the place in the universe with most stars packed in 5 parsecs, do you still think that's true? Because I think it's actually the center of ellipticals with 400 km per second velocity dispersions that have an even much higher physical density. So, yes, if you take the whole stellar system and you define your stellar system as the nuclear cluster, then it's...
So I would argue that in the center of a big elliptical, in the central 5 parsec, you basically have a black hole. And in the biggest elliptical galaxies, you destroy the nuclear star cluster. So they get evaporated, like Matthias was asking. So there is really probably encounter with a black hole, and it would make your cluster disappear. So I would still argue that packed in 5 parsec radius, those are still the densest systems.
Right. And if you just interpolate the light profile all the way in, then you get a higher number for the ellipticals. But the question is, as you say, what happens in the central 10 parsecs? Maybe there's cores there, so
Yeah.
cores maybe. But cuspy ellipticals?
Yeah, maybe they're completely density.
When you look at MX7, there is absolutely no nuclear cluster.
Not MX7.
Okay, is there further questions? No? Then we had already very lively discussion. So let's thank Nadine again.